Today, we're going to dive into a pretty incredible STEM curriculum. It takes students on this amazing journey, starting with just a simple spark of electricity on a piece of paper and taking them all the way to launching their own rockets. It's all about turning that raw curiosity into real, hands-on engineering skills, one project at a time. So let's just jump right in with a huge question, right? One that feels, super complex, maybe even impossible if you're just starting out. How do you build a rocket? Your mind probably goes to complex machinery, aerospace engineering, maybe a whole team of scientists in lab coats. Well, believe it or not, the answer is way simpler, and honestly, a lot more profound. It all starts with a single piece of paper, and that is the core idea behind this entire learning philosophy. You start with the most basic, accessible materials to build something truly incredible. Let's see how it all kicks off. Okay, so our journey begins right here, with a little spark of genius. Before anyone even thinks about building a rover or a rocket, they have to get the hang of the absolute fundamentals. And that means learning how to make electricity do what you want on a simple sheet of paper. What's so cool about this approach is how it makes electronics feel so easy. Instead of some intimidating complex breadboard, students are just laying down some conductive tape, connecting a tiny little LED, and popping in a small battery. And just like that, in a matter of moments, they've created light. They've built their very first functioning circuit. And it gets more advanced fast. They start using this material called velostat, and suddenly they can turn a basic on-off switch into a pressure-sensitive touch sensor. It's such a powerful lesson right at the beginning that even the simplest components can create these really interactive and sophisticated results. All right, so once the students have mastered the basics, where do they go from there? Well, they immediately start putting those skills to work, turning those simple paper circuits into all sorts of wild and imaginative gadgets. And the sheer variety of projects is just incredible. I mean, we see everything from do-it-yourself book lamps to motorized spin art robots. A younger student might build a simple little flashlight, but an older one could create a super complex multi-circuit jellyfish that lights up. It really shows that engineering isn't just about being technical. It's a tool for art, for imagination, for storytelling. Now we get to what I think is the real heart of this curriculum, the evolution of a single powerful idea. This section is all about the journey from a simple cardboard vehicle to a complex, programmable robot. It's such a clear and powerful progression of skills. You can see how the learning curve is mapped out in these really clear stages. It starts with a basic cardboard chassis, just learning about motors and solar power. From there, they build a paper rover that's actually controlled by a smartphone, and eventually, they graduate to a full-on 3D printed rover that requires soldering and programming a real microcontroller. It's like leveling up in a video game. And this brings us to a really, really clever insight. How do you introduce robotics without totally overwhelming students with complex coding? The answer is brilliantly simple. You use the smartphone that's probably already in their pocket as the robot's brain. So how on earth does that work? Well, it's ingenious. The phone screen just displays simple black and white patterns. The rover has these little light sensors that literally read those patterns right off the screen. A white block tells the motor to go, and a black block tells it to stop. It's this incredibly direct link between the phone and the rover, all controlled by light. And this is so important because it just completely removes the cost barrier and that steep learning curve of traditional microcontrollers. It makes robotics accessible to pretty much anyone with a phone. All right, now for the grand finale. This is where all the skills, the paper circuits, the mechanics, the programming logic, the troubleshooting, where everything converges into one ambitious, high-flying project. It's time to launch into the future. And now we're back to building that rocket. Students create a water rocket from a simple plastic bottle. But here's the twist. The real engineering challenge isn't the launch, it's the recovery. They have to design a whole parachute system with a special nose cone that pops off right at the rocket's peak. Every single launch becomes a real-world experiment in physics and aerodynamics. But, building the rocket is only half the mission. The next question is obvious. How high did it actually go? And this is where math becomes absolutely essential. Students use this trigonometric formula to calculate their rocket's altitude, turning what looks like an abstract equation into a super practical tool for measuring their own success. And get this, they don't just use the formula, they actually build their own tools to solve it. They use the coding platform Scratch to program their very own altitude calculator. They even use Gemini AI as a sort of coding partner to help them work through the math. So when they're out in the field, one student is using a clinometer to measure the angle, another is measuring the distance, and then they plug those numbers right into their own custom-built mission control software. How cool is that? So after all this building and coding and launching, what's the ultimate goal here? What's the real takeaway? It's not just about learning how to build a specific gadget. It's about developing a powerful new way of thinking. These right here, these are the true skills that get unlocked. Through every short circuit, every failed launch, and every single coding bug, students are learning critical thinking. They're learning to integrate hardware and software, to design and redesign, and most importantly, they're learning to be resilient. This is the maker mindset. It's the belief that you can solve pretty much any problem by building, testing, and trying again. Which leaves us with one final and kind of mind-blowing question. If a journey this complex, from circuits to software to aerospace physics, can really begin with a simple piece of paper and some tape, where does it end? What are these young engineers going to build next?